Thank you for reminding me. So that's one important keep ideas. If we have exponential sequence r to the n, if the base is between -1 to 1, not including the endpoints, then it will be convergent to 0. It will be convergent to 1 if the r, the ratio, is exactly 1. In fact, 1 to the n is equals to 1 for every n, right? For every n. Now, then it will be divergent, for otherwise. In fact, I want to say divergent to infinity. It will be infinity for r greater than 1. It will be divergent for r less than equals to -1. So if we look at the number line, between -1 to 1, right? It will be convergent to 0 here. It will be convergent to 0, It will be convergent to 1 here. And then this part here will be divergent to infinity. And the one here, it will be simply divergent. Why don't you say divergent to negative infinity, Thomas? Well, because it's not divergent to negative infinity. Now take a look, for example, if we have -2 to the n, the sequence will be -2, 4, -8, 16, -32, 64. So you see that the magnitude, the absolute value, goes to infinity, but it is alternating, as if when I try to graph the sequence, it is actually like this: -2, 4, -8, 16, as if it is actually growing exponentially by 2 to the x, but alternating positive, negative, positive, negative. You see? It's like that. So if you go further, then it will converge to not positive infinity. It may also converge to negative infinity. In other words, it's not convergent anywhere. Okay? It's not even divergent to infinity in that sense, no. Okay? It's not even divergent to infinity. So when the r, the ratio, is -1 or less than -1, this will be the limit does not exist. Limit n goes to infinity of -2 to the n does not exist, and therefore we call that divergent. Okay, that's the first concept from this r to the n. Now you can imagine this r to the n using our exponential function. Too bad exponential function only allows the base to be positive and not 1, right? Okay, but you can imagine what happens if it is between 0 to 1. Between 0 to 1, it will be decreasing. Therefore, when x goes to infinity, it will be decreasing down to 0. When r equals to 1, it's already constant function y equals to 1. So it's always 1. What happens if the r, the base, to be greater than 1? Then it will be increasing to infinity. Okay, we call that divergent to infinity. Now that's the first important concept on ratio or exponential sequence. Second definition, a sequence a sub n is increasing if a sub 1, actually I don't want to say that, if a sub n is less than a sub n plus 1 less than a sub n plus 2 and on. For n greater equals to 1. So starting from 1, basically a sub 1 is less than a sub 2, less than a sub 3. The sequence actually keeps on going up. Okay? That's when we say the sequence is increasing. Now, similarly, we say a sequence is decreasing if a sub n is greater than a sub n plus 1 is greater than a sub n plus 2, so on and so forth. For n greater equals to 1. Okay, pictorially, suppose this is our graph. Now a sequence is increasing. You know what? Let me use another color. Let me use this color. A sequence is said to be increasing if, let's say this is the first term, it keeps on going up. Okay. Now, if you think about this, you can say that if you kind of like look at the underlying, the superposition function, you will see that the function is increasing, and we can detect that by looking at the first derivative. The first derivative of the superposition function is positive, right? Now, remember, we cannot do the derivative for sequence because sequence is not a continuous function. Therefore, the limit does not exist. It's not even continuous. Okay, so we can't talk about the limit at any certain value x. We can talk about the limit at infinity, but not at certain value x. Okay, so therefore we cannot do the derivative of a sequence, but we can look at the superposition function. Now, a sequence is decreasing if from the first term to the next term, it keeps on going down. You see what I mean? So this is the decreasing trend, and this has increasing trend. Okay. Now, implicitly, I told you one technique to show that a sequence is increasing or decreasing. Maybe I say this more. A sequence is monotonic. if it is either increasing or decreasing. That's my notation for increasing, decreasing. Now, to check for monotonicity, the first method, we have get the superposition function fx and show that f prime x is strictly greater than 0 or strictly less than 0. That's something we learned from calculus 1. Second is to show that when n is less than n plus 1 implies a sub n is less than a sub n plus 1. So when you go one term higher than the previous term, then the next term is greater than the previous term. This is to show increasing. To show increasing, and to show decreasing. To show decreasing, we show that the current term is greater than the next term. Okay, that's to check monotonicity. In the next two examples, we have these examples in the book. We have these two examples in the book. For example, show that this sequence, 3 over n plus 5, maybe I use n squared plus 5, why not, is decreasing. Show that this is decreasing. I will show you two different ways to do this. Okay, solution, the first one. The first method, I start with this, 3 over n squared plus 5. This is greater than 3 over n plus 1 squared plus 5. Therefore, a sub n is greater than a sub n plus 1. Is it right? Even though, hold on. I'm not done yet. No. We have issue here. How do you come up with this, Thomas? Do you agree that's true? If you divide by something larger, then the quotient will be smaller. Do you agree with that?
Yes.
Okay. Now, the thing is, saying that this is true does not show how you know that's true. That's the conclusion we're supposed to get. That's not the starting point, though. Okay, that's not the starting point. Now, we will argue in the following way. We will start with, well, we know that n is less than n plus 1, right? Therefore, n squared must be less than n plus 1 squared. Is it right? Now, n squared plus 5 must be less than n plus 1 squared plus 5. Now, both of them positive. Therefore, when I do the reciprocal, it is still positive. Actually, I don't need that there. I need that here. 1 over n plus 1 squared plus 5. That will be positive. Now, then multiply by 3 both sides. I get the nth term and n plus first term. So you need to carry from the original n is less than n plus 1, implies this, implies this, implies this, implies this, implies this, and therefore you claim so a sub n is decreasing. Okay, at least we know what we need to show. We need to show this. Okay, but saying that's what you need to show doesn't mean you already show it. No, you need to show why this is true, and the way you argue is this one. So, chapter 11 is difficult because it is more about how you argue your case instead of finding the answer. Okay, so I'm not asking you if this is increasing or decreasing. I'm asking you, why is it decreasing? And then if you show, oh, because of this, well, you are saying, it's like you're answering my question by questioning my answer. How to say that? It's like asking this. It's like asking this. But this is a serious question, though. Why is 0 less than 1? My professor asked this question when I was in senior level in my undergrad. When I was in the 4th year, my professor asked this question. And this question required 4 pages to answer. I mean, we all know 1 is greater than 0. If you don't know this, that 1 is greater than 0, drop the class. We all know that. We all took it for granted. But we needed to prove that in one of my, I think it was my first midterm of real analysis class. Have you ever think about it? How do you argue that 1 is greater than 0? Oh, because it is on the right-hand side, because it is on the right-hand side of the number line. Yeah, then why don't we do the number line like this then? That still means 1 is greater than 0, but it is on the left-hand side. In fact, to argue that number line has to be like this is discriminatory against those who are left-hand people, like me. I'm a left-hander. Why it always have to go to the right? Of course, I make up stories, right? Okay, but I make up stories that if anybody dare enough to say that it has to go to the right, then I will call that discrimination. Then I have a lawsuit and make money, right? No. That's not a good argument. The argument, actually, oh, by the way, the argument will be first, I need to show that 0 is not equals to 1. How do you show that? But that's basically the first thing you need to show. You need to show that 0 is not equals to 1. Second, by trichotomy, because 0 is not equals to 1, then 1 is either less than 0 or 1 is greater than 0. See, a number is either a real number is either positive or negative or 0. Okay, so maybe to be more precise, if 1 is not 0, which we are supposed to prove in the first step, the second step then, 1 is positive or 1 is negative. Now, the way we argue is we are not proving that 1 is not negative. We are actually going forward. If 1 were negative, then 1 squared will be positive, because negative times negative is positive. 1 squared is still positive, but 1 squared is equals to 1. So even if 1 is negative, 1 squared, which is 1, is positive and therefore greater than 0. That's the big line skeleton of the proof. But yes, I proved that in 4 pages. Everybody in that class had a nightmare because of that question. Well, anyway, that's the first way to prove. Okay, so it's not that I don't need you to just tell me, oh, because this is true. I will ask why. If you just show me that, then I will ask why. Give me the reason why that's true. Okay, but Thomas, that's obvious. What is obvious for you is not obvious for me. And dare you not use that argument, because I may show you my work without showing, I may show you the solution of a question without showing you the work, and just say, don't you think that's obvious? You see what I mean? Okay. What is obvious for you may not be obvious for me. Actually, most of the time, it's the other way around. What is obvious for me may not be obvious for you, right? Okay, so no, don't use the argument that it is clear, unless it is really, really, really clear, like this one here. Okay, that one is clear. Okay, now the second way to prove this is you use superposition function. Let fx equals to 3 over x squared plus 5. And then you do the, and then note that fn equals to 3 over n squared plus 5 equals to a sub n. That's how you say that for the integer domain, positive integer domain, this function actually is the sequence. Now then, do the first derivative. This will be x squared plus 5 being squared. On the top, I will get 0 minus 3 times 2x only. So that will be negative 6x over x squared plus 5 squared. Now, how do you argue that this is decreasing? This is negative. Well, x squared plus 5 is always positive. Is it right? Note. Now, where for x greater equals to 1, negative 6x is less than equals to negative 6, which is negative. So, for x greater equals to 1, f prime x is negative. Okay, so basically the function is decreasing when x is greater equals to 1. That's all you need to show. You don't need to show that the function is decreasing all the time from negative infinity to positive infinity. You don't need to. You just need to show that on this part here, on the region where the sequence applies, the function, the superposition function, is actually decreasing. That's all you need to show. Okay? Now then, so Fn is I'm sorry, not Fn, the sequence. So the sequence A sub n is decreasing when n is greater or equals to 1. Okay. Now there is one terminology that our textbook does not mention, and let me just mention it right away, right now. A term called eventually. Eventually. The term called eventually means after some n, some term, then the following apply. Let's say, for example, a sub n equals to n squared minus 10n plus 1. If you take a look on this sequence, when n equals to 1, that will be -8. And you will see it's actually going down, but eventually it goes up, right? Okay. Now, you cannot say that this sequence is decreasing or increasing. No. This sequence is not increasing. Why it's not increasing? Because it is increasing, but it doesn't start from the first term. The first couple of terms, it is decreasing. Only after some terms, it is increasing. I mean, you can imagine this is quadratic, right? With vertex at 5 comma something. Okay, but because it is decreasing in the first couple of terms, then we cannot call this sequence increasing. Okay, now, of course, we also cannot say this sequence, is decreasing. Why? It is decreasing only in the first couple of terms. Okay, but we can say this sequence is eventually increasing. Are you with me? In fact, we can say a sub n is increasing, eventually increasing for n at least 5. Right? Now, this is my notation for eventually increasing. That's my notation. Okay? It's not in the book. It's not in the book. Now, likewise, if you see eventually decreasing, when we say eventually decreasing, you may have a sequence that looks like this, like at the beginning it goes up, and then eventually it goes down. Okay, now this is eventually decreasing. The phrase eventually decreasing means the following. After some integer, positive integer n, the sequence is going down. In other words, it doesn't start from 1, but it starts from some number, some term greater than the first term. Okay, now I will use this term eventually in that sense. And it is actually the correct words we use. Is there a way to say that a sequence is decreasing only in the beginning, or do you say that it is eventually increasing? We say it is eventually increasing. There's no terminology we use for a sequence that is decreasing only in the first couple of terms. Now, actually, the reason we don't care about the first couple of terms because the main purpose of this section is what happened with the sequence at infinity. So you will see, it doesn't matter what happened with you at the beginning. What happened is later on when it is at infinity. Okay, now the decreasing or increasing property, the monotonicity property of that sequence will be used in our later theorem. Let me go on. Another note, definition. A sequence A sub n is bounded above if there is a number m where actually such that, I should say, such that A sub n, the term, is less than equals to m for n greater than 1. It's basically we have the following situation. Let's say you have sequences that look like this. Now notice that this sequence is bounded above by a number m. Of course, if it is bounded above by a number m, then it must be bounded above by another number greater than m, right? That's, in other words, when I say bounded above, if there is such number, that number doesn't have to be unique. All you need to show that for every sequence, every term, it's bounded above. Now, of course, we can also twist the definition for bounded below. Okay, let me call that with lowercase m for minimum. Okay, so bounded below if there is a number m such that A sub n is greater equals to that lower, the minimum, for all terms. Yeah, of course, then when we say a sequence is bounded. When we say it is bounded, it means it's bounded above and below. Now, of course, we can also use the phrase eventually in this case. Right? When we say a sequence is eventually bounded by something and something. Let's say for example, the sequence, what is good? 1000 over n. This is bounded below by 0. It's definitely bounded above by 1000, right? So this sequence is bounded, okay? But I will say that this sequence is eventually bounded above by, let's say, 100. Can I say so? Yeah, it is eventually bounded above by 100. It means there is an n, there is a number, the term, where when the term is greater than that number, in this case, the 10th term. Starting from the 10th term and on, this sequence is bounded above by 100. You see? So, I use an illustration where this sequence is bounded already, right? But it's bounded by a big number. I want to say that it is eventually bounded above by a much smaller number. Okay, but it doesn't start from 1, it starts from 10 here. So we can say this sequence, 1000 over n, is a sequence that is eventually bounded above by 100. Does it make sense? Okay. That's just definition of bounded, bounded above, bounded below, increasing, decreasing, and eventually. Monotonic sequence theorem, important theorem. Monotonic sequence theorem. I will not prove this. I just give you the idea. It says the following: every bounded monotonic sequence is convergent. So imagine if I show you the worst case. If a sequence is bounded above and below. So if it is bounded above, and bounded below, and the sequence is monotonic. Let's say it's monotonic increasing. So because it's bounded, eventually they will converge in there, right? Actually, it doesn't have to be there. It is possible that this upper bound is somewhere else, even higher. And the sequence actually converge into somewhere less than that. But you see, this argument, the full proof is in the book, and it requires what we call completeness axiom. That's kind of like axiom is not a theorem. It's axiom is a rule that we know is true without proving, without the need of proving. Now, completeness axiom basically says that on the number line, on a real number line, okay, if you have upper bound, a lot of upper bound, upper bound, upper bound, upper bound, there must be a smallest upper bound, smallest upper bound, or the least upper bound, our textbook called it. If you have a bunch of upper bound, there must be one of them that is the smallest, such that any number to the less of less than that is not an upper bound anymore. Okay, that's what the theorem says. Now, I'm not going into the theorem in the proving of the theorem. I want you to actually look at the intuition of the theorem. Notice that this theorem is overkill. This theorem is overkill. We don't need that to be bounded above and below. No. You see that this theorem actually works if you have the following. If it is increasing and bounded above. Can you follow me? If it is increasing and bounded above, then it must be convergent. If it is decreasing and bounded below, then the sequence also convergent. Does it make sense? So imagine if your sequence actually start from here going down. Right? And you see this conversion? Now the thing is, even though I said earlier that it's overkill, that all you need is actually it is increasing and bounded above, right? But if a sequence is increasing, take a look. If a sequence is increasing, then the starting point must be the lower bound. In other words, any increasing sequence must be bounded below. Our textbook didn't say that. Increasing sequence must be bounded below. Decreasing sequence must be bounded above. Right? Okay. Decreasing sequence, because it is decreasing, then the first term must be the highest one. That's the upper bound. Right? Okay. So basically saying that it is increasing or decreasing already set a bound. All you need is another bound. Increasing means implicitly is bounded below. Once it is bounded above, then it is convergent. Decreasing means it is bounded above. Like all you need is extra bound below to squeeze it. Okay, now that's why when I say monotonic sequence theorem here, that every bounded monotonic is convergent, when it comes to the proving, you will see we just need to show that it is, for example, increasing and bounded above, decreasing and bounded below. Now, if you really want to be strict with this monotonic sequence theorem where it is bounded, which means you need to get the upper bound and lower bound, okay, then your lower bound will be one of the first term. Okay, let's apply this. Let's apply this. Let's apply this theorem. Suppose, for example, let me see which one can I use. Number 72. Is it number 72 good or 74? 74. Let me do number 74. Number 74. A sub n equals to 2n minus 3 over 3n plus 4. Determine whether the sequence is increasing or decreasing or not monotonic. Is the sequence bounded? Which way you want to go? Do you think it is increasing or decreasing? Let's see. Let's take a look on the first couple terms. When n equals to 1, a sub 1, that's negative 1 over 7. A sub 2, that will be 1 over 10. A sub 3, it seems to be increasing, huh? But I'm not sure. When n equals to 3, this is 3 over 13. Nah, I don't get any pattern. I don't get any pattern. Yes. So imagine this is my scratch paper. Okay. Let's do superposition function then. Let fx equals to 2x minus 3 over 3x plus 4. Note that fn equals to 2n minus 3 over 3n plus 4, which is the nth term. Now get the first derivative. That's 2 times 3x plus 4 minus 3 times 2x minus 3. That is 6x plus 8 minus 6x plus 9 over 3x plus 4 squared. That's 17 over 3x plus 4 squared. Notice that this is positive for x at least 1, right? Okay, let me continue here. So fx is increasing for x greater equals to 1, and a sub n, the sequence is increasing for n greater equals to 1. Is it okay? So I was trying to sketch that. It seems like it's confusing for me, so I cancel doing this. Ooh. So now I have shown that this sequence is increasing. I have shown that this sequence is increasing. Can I show that this sequence is bounded above? Can you pick a number that it is always greater than that a sub n? So step 1, I say claim fx, I'm sorry, the sequence is increasing. That's the proof. The second thing I want to show that it is bounded above. Can you guess a number? Claim that a sub n is bounded by some number. Let's say 2. Okay, let's say 2. I just need to show that it is in monotonic increasing. Okay, and bounded above, right? Claim that this sequence is always less than equals to 2. Let's prove it. Proof 2n minus 3 less over 3n plus 4 less than equals to 2 for n greater equals to 1. If and only if 2n minus 3 less than equals to 2 times 3n plus 4, 6n plus 8. So 0 is less than equals to 4n plus 11. Right? If and only, and this is true for n greater equals to 1. Okay. Okay, because this is true, then this is true, then this is true, then this is true. Okay, because, let me continue, since the sequence is increasing and bounded above, then the sequence is convergent. But when you come up to this conclusion, you need to code why. Then by monotonic sequence theorem. So it would be nice if you can memorize the name of those theorems also. Okay, actually I prefer to say it this way. Then by monotonic sequence theorem, A sub n is convergent. I prefer to say it this way. Mathematical notation. I get a lot less lazier, so let me teach you some math symbols and what it means. Now earlier I showed you this is increasing, this is decreasing. Do you need further explanation for that? Is the notation clear? I actually use that notation even in my calculus 1 when I substitute for somebody. Okay, I use this notation for concave up. I use this notation for concave down. Now I will use eventually increasing using this notation, eventually decreasing this notation. Okay. And these notations, even though I say I use that in my class, you don't see it in the textbook. But the further you go into math, especially graduate study, then you will see more and more instructors using them. Next, I will use this notation for convergent. And I will use this notation for divergent. I know not a lot of teachers actually using this notation. It's very minimum, very minimum. If you see any teacher using this notation, that teacher must be lazy. More. This notation means for every. Backward E means there exists. In fact, backward E with exclamation mark means there exists uniquely. And this notation means such that. Of course, the following notation, this is element, you know this, element, you know what, that's a common one. So let me put it on the first row. This is element, this is subset, right? Okay, in fact, this means contains. It's actually just element notation going backward. When I say 3 is an element of a natural number, then natural number contains 3. Okay, now the thing is this notation contains 3. When you write it too small, may look like this, may look like such that. No, the such that has this phenomena. It's not curvy like this, but it's curvy up like that. And then the line is not horizontal. No, it's not. The line is not horizontal. It's slanted up like that. Okay, those are some notations. Okay, let's say the following. Do you remember the definition of limit? For example, how to use this notation, right? Definition of limit. We say limit x approaching a of fx equals to L if and only if for every epsilon positive there exists delta positive such that the magnitude or the distance of the fx from L is less than epsilon whenever the distance of x from A is less than delta. Now let's use R notation. Are you ready? Limit x approaching A of fx equals to L if and only if for every epsilon positive there exists delta positive such that whenever the distance of x from A is less than delta, we will get the distance from the function fx from L less than epsilon. Now, when I did my graduate study, my textbook is very thin. It's less than 500 pages. But my professor went over one page for 50 minutes because of this. Because of this. Instead of 2 lines, the language suddenly becomes Klingon. Okay, let's see more. Let's see more. Let's see more. Suppose, actually, let me see number 56. Number 56. This may not be something I prove using what I taught you today, but I want to go over this anyway. So the sequence is -3 to the n over n factorial. The question is, determine whether the sequence converges or diverges. Solution. Let's do some scratch work first. A sub 1 is -3 over 1. A sub 2 is -3 squared, which is 9, over 2 factorial, which is 2. 3 The top one you keep on multiplying by 3, but the bottom one you keep on multiplying by the term. Correct? So you will see that even though the top one keep on multiplying by 3, the bottom one is multiplied by larger number, right? Multiplied by n in general. So let's see some pattern here. Let me do the following. Let me say absolute of a sub n. That's absolute of negative 3 to the n over n factorial. That will be 3 to the n over n factorial. Is that right? This way, I don't need to take care. The positive negative. Now, can you tell if this actually converges to what? Now, you will see eventually this will be 3 over n times 3 over n minus 1 times 3 over n minus 2 all the way to 3 over 3, 3 over 2, 3 over 1. Is that right? Can you follow me? Now, notice that for n greater than 3, for n greater than 3, you will see that 3 over n is less than 1. So right? Actually, I want to say that 3 over n, make it 4 here, 1, 4 or more. So you need to be able to argue your case though. So 3 over n minus 1 will be less than or equal to 1. Right? So now we can say further that absolute of the n term is equals to 3 over n times 3 over n minus 1 all the way to 3 over 3, 3 over 2, 3 over 1. This is less than equals to 3 over n times, I will compare this to 1. Compare that to 1. And this will be 1, 3 over 2, 3. Which means this is less than equals to 27 over 2n. Right? But what is this convergent to? Converge to what as n goes to infinity? Converges to 0. Right? Are you with me? How do you get that 27 over 2n times? The 27 comes from these 3 times a bunch of 1s multiplied by 3 by another 3. That's how I get that 27. The 2n is the denominator n times 2. That's how I get that. My issue is then what kind of conclusion you can take from here? You can say then limit n goes to infinity of absolute a sub n is equal to what?
0.
Now the key part is why. You need to mention the reason. How did you get all ones? As long as the n is greater equals to 4. So what happened is the first term is 3 over 1. The second term is 3 over 2 times 3 over 1, 3 over 3, 3 over 4, 3 over 5, and so on. Right? Okay. So the last two terms, I keep it as is. Okay, the last two terms, I keep it as is. 3 over 2, 3 over 1. Now, the first term here, I keep it as is, 3 over n, right? Because this keep on going to 3 over n, right? Maybe I kind of like move it away. I will say this is 3 over n. Now, everything here is less than 1. Right? So I can rightfully say that this is less than 1, less than 1, less than 1. So this is less than 1. 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 I keep this 3 half. I keep this 3 over 1. And I keep this. Does it make sense right now? Okay, that's the explanation of what happened there. Coming back here. What is the reason then we can say that the limit of the absolute is 0? It is true the right-hand limit goes to 0. What makes it this? What makes this goes to 0? No clue? I squeeze theorem. Because implicitly absolute of something always greater equals to 0. Now consequently, if limit of absolute something is 0, then that thing must be 0. Okay, we have one theorem like that before. We have one theorem like that before, theorem 6. That is on page 718. I think the one I proved by squeeze theorem also. I proved that by squeeze theorem also. A sub n is bounded above by absolute of a sub n and bounded below by negative absolute a sub n. Now, if this goes to 0 and this goes to 0, then by squeeze theorem, a sub n goes to 0. Number 76, I jumped around. Number 76. a sub n equals to n e to the power of negative n. Ooh, this one is nasty. The question is, part A, is it increasing, decreasing, or not? Part B, is it bounded? Is a sub n bounded? So solution, part A, do you want to say that it is increasing or decreasing? A sub n, basically n over e to the n, right? So you see that the bottom one, the top one is increasing linearly, but the bottom one is increasing exponentially. So we expect this to actually, the denominator goes to infinity a lot faster, right? So we expect this to go down to 0. Okay, we expect this to go down to 0. But how to prove this? We have n, I need to compare n and e to the n. This is always true though, right? This is always true. Do you think so? So when n equals to 1, that's true. When n equals to 2, it's true, and so on and so forth. So later on, we'll have n over e to the n is bounded above by 1. And both of them positive, so it's bounded below also. Okay, then part B is actually solved, right? But how should we show that it is decreasing plane? A sub n is decreasing. Proof. So you see what I did here on the right-hand side? That's my intuition. Proof. Let f(x) be the superposition function x e to the negative x. Note that fn equals to n e to the negative n, which is the nth term. Then the derivative will be e to the negative x plus, actually, x e to the negative x times negative 1. So this is e to the negative x minus x e to the negative x. Factor e to the negative x, 1 minus x. Right? Notice that. Note that e to the negative x is always positive. I mean, yeah, for every x. And 1 minus x is negative for x greater than 1. I think I should say greater equals to 1. So f prime x is negative, which implies the function is decreasing, and therefore the sequence is decreasing. Second, claim it is decreasing. So we actually don't need to prove, that it is bounded above. Since it is decreasing, all we need to show that it is that the function is bounded below. I want to say that it's bounded below by 0. It's positive after all. Why? Proof A sub n equals to n over e to the n is at least 1, e to the n is at least 1. So A sub n is at least is strictly positive. All you need to show that is yeah, it's strictly positive. So A sub n is bounded below. Now, since the sequence is decreasing, implicitly it is bounded above. So A sub n is bounded above by the first term. Is it right? Don't you think so? Together with this, it's bounded below. So A sub n is bounded above by the first term. It's bounded below by 0. Right? So the sequence now bounded and monotonic. They don't tell us to come up to this conclusion, but we actually can do so now by monotonic sequence theorem. A sub n is convergent. In fact, we can say more. A sub n is convergent to 0. The formal way of writing is basically just A sub n converges to 0 as n goes to infinity. But how do we know it is convergent to 0 though? Hold on. How do we know it is convergent to 0? I didn't prove that. All I know that it is decreasing. All I know that it is decreasing and bounded. So hold on. This requires some proof. Why? Then I actually need to do this though. I need to do limit n goes to infinity of n over e to the n, right? But I don't think I can do that. I cannot use L'Hopital rule at this point. Proof. Look at limit of the superposition function. The reason I get the superposition function so that I can use L'Hopital rule. So as f(x) converges to 0 as x goes to infinity, then A sub n converges to 0 as x goes to infinity, as n goes to infinity. Notice that the blue part here can be done. I can show that this sequence is convergent. I can show that this sequence is convergent without showing that that sequence is decreasing, without showing that the sequence is bounded. Okay. In other words, monotonic sequence theorem only shows that it is convergent. It doesn't show where it converges to. Okay. What I did here requires further proof. Let me give myself a break. I come back at 8. 55. And at that time, I will do more problems from here. Some of them actually quite interesting. Yeah, some of them actually quite interesting. Thank you. Thank you for reminding me. Yeah, number 79, find the limit of sequence, square root of 2, square root of 2, radical 2, square root of 2, radical 2, radical 2, and on. To prove this in a more, how to say that, a more sophisticated way is actually quite difficult, because I'm supposed to show the following. I need to first show that the sequence is increasing. Okay, I need to first show that the sequence is increasing, and then it's bounded. Therefore, by monotonic sequence theorem, then the sequence is convergent. Now then, once the sequence is convergent, then I can assume, I can say let A sub n convergent to L. Okay, but suppose that's what I call L. So proof. I mean, not proof. That's supposed to be solution. Solution. When they say find the limit, in this case, it sounds like the limit already assumed to exist. So let's say let limit of n goes to infinity of the sequence be L. Notice that the nth term, n plus first term, is equal to, I wonder if you see the pattern. If this is the nth, the nth term is, the next term is like that. If this is your previous term, then the next term, that previous term is here. Do you notice that? So we can say that the next term is square root of 2 of the previous term. Is it right? Square both sides is the n plus first term squared equals to 2 times a sub n. Now apply the condition of limit. Limit n goes to infinity of n plus first term squared equals to limit n goes to infinity of 2 times a sub n. Now tell me, what do we have on the left hand side? Limit n goes to infinity of the n plus first term being squared. Right? This is 2 times limit n goes to infinity of the n term. Now notice that the limit of the sequence is L. Is it right? The limit of the sequence is L. So I can say this is L squared, this is 2L. Fast forward and continue on the right hand side. Fast forward, you will see either L equals to 2 or L equals to 0. But the nth term always positive. It won't be 0. It is convergent to 2. So we do it actually from the parent. Now, notice that when I do the solution here, I did assume the limit exists. I did assume that the sequence is convergent. But if the question were proof that it is convergent, then I'm supposed to go here. I'm supposed to go here. This is what I'm supposed to do. At least that's one of the things I'm supposed to do. Okay. I think in this case, yes, it is increasing and it is bounded above. You can show that it's bounded above by, let's say, 3. Okay. A more detailed analysis of that can be seen on number 80. Think about this. Okay. Now, your suggested homework from this section will be why I
Wait, why does the left-hand side equal the L squared?
oh, so why is this true? Give me a second. I wonder why my computer is not reacting well to it. Okay. Why is this L? Oh, that's because of this. That's because of this. You see that limit of n goes to infinity of a sub n equals to L, right? So what do you think the limit of the next term?
Oh, okay. That makes sense.
Does that make sense? Then it must go to L actually faster, right? Okay, that's actually the property I use, and it was actually proven in number 78. That's number 78. They ask you to prove if it is convergent, show that the limit of the next term equals to the limit of the previous term. Well, it's the limit. It's the limit. So once they all goes to infinity, doesn't matter who comes first, who comes later. Okay, the next section, 11.2. This is the start of disaster. 11.2 is a long section. It is a long section. So 11.2, that's on series. What are the things I need to do in this section? Yeah, like what I say, this is a long section. I need to first, things that I need to explain here is infinite series, partial sum, convergent, divergent series, sometimes it's just about terminology, and then geometric series. Of course, we have more. Yeah, of course, we have more, which I don't think I have time to cover later on. But let me just do this first. Okay, call this part A. I will start with definition. Let A sub n be an infinite sequence. Or simply a sequence. n first. The sum, now the sum notation here, not E, not like that. Please don't write it this way. It should look like a capital block M that you rotate counterclockwise 90 degrees such that it becomes this. Okay, now the sum of A sub n from n equals to 1 to infinity is called the infinite series. We call that infinite series. Second, the sum for the sequence from 1 to n is, this basically means a sub 1 plus a sub 2 plus a sub 3 all the way to a sub n. This is where you start. This is where you end. Denoted by S sub n is called nth partial sum. Now this infinite series, sometimes also written by convention, is also written the sum of a sub n only. Now if we don't have where the start and where it ends, it means it starts from 1 and goes to infinity. Okay. In other words, if you don't see any notation here, it means it starts from 1 goes to infinity. That's what it means. Okay. If it is not starting from 1, it is not going to infinity, then you need to write it down. Okay. Now, in my class, I want you to write it down. In my class, I want you to write it down. So let's see. Notation-wise, so for to explain the idea, the sum of a sub n from 1 to infinity, I call this index. This is just the indexing. This is the indexing, means start from 1 goes to infinity. Okay, now that notation has exactly the same meaning to, if I change that n to the I, or to the j. Which means a sub 1 starting from 1 up to infinity. Now, S1 means just the first term. S2 means the sum of the first two terms. S3 is the sum of the first three terms. Okay. Sn means the sum of the first n terms. That's the partial sum. Now, notice that this partial sum, this partial sum forms a new sequence which we call that n partial sum term. a new sequence that we call the n partial sum. Sequence of n partial sums. If Sn is convergent, if Sn is convergent, then we use notation Sn convergent to S. And that's the same to the infinite series. Let's practice with this. I hope by doing so, you kind of like imagine what we are dealing with. For example, let's say I have the sequence, consider the sequence, let's say 3 to the negative n. We usually write it this way. So the first term is 1 over 3, 1 over 9, 1 over 27, 1 over 81, 1 over 3 to the 5th, and on, right? Okay, now then, so what is S1? S1 will be just the first term. You will see the first partial sum is the same to the first term. S2 will be 1/3 plus 1/9. S3 is 1/3 plus 1/9 plus 1 over 27. Okay, now we will show later on, we will show later on that Sn is convergent to 1/2. Okay, but that's later. Well, you learned that it actually in algebra 2. This is geometric series. Okay, now this 1/2, because it is convergent, then we call the series equals to 1/2 because it's convergent. Okay. Geometric series. Maybe I give you geometric sequence first. Geometric sequence has the pattern a sub n equals to the first term times r to the n minus 1. Geometric sequence is a sequence with common ratio. Where the next term over the current term always have the same ratio. So if you kind of like look at the structure, the first term, the second term, the third term, and on, you keep on multiplying by r. So the second term is the first term times r. The third term is the second term times another r. The fourth term is the third term times another r. So you see the pattern here that, like, let's say the fifth term will be the first term times r to the fourth, right? You keep on multiplying by r, multiplying by r, multiplying by r. We call that geometric sequence. We call that geometric sequence. Now we want to show that the geometric series is the sum of the first term r to the n minus 1 from n equals to 1 to infinity. We want to show that this is convergent to a sub 1 over 1 minus r when the magnitude of r is less than 1. Proof. As sum n, the n partial sum will be the first term plus the second term plus the third term all the way to the nth term, which is the first term plus the first term times r plus the first term times r squared all the way to the first term times r to the n minus 1. So I basically do this kind of parallel. I do the substitution. Okay, that's my nth partial sum. Now, the thing is, if I multiply by this nth partial sum by r, then this guy here will multiply by r. 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 Now I will subtract both sides. Then on the left-hand side, I will get the n partial sum minus r times the n partial sum. On the right-hand side, notice that the middle terms cancel. I only have the first term minus the last term. So n partial sum times 1 minus r is equals to the first term times 1 minus r to the n. So the n partial sum for any geometric series is given by the first term times 1 minus r to the n over 1 minus r. Actually, that's already one result. That's already one result. Furthermore, we know that when r is between -1 to 1, not including the endpoints, r to the n is convergent to 0, right? Or to be more precise, when magnitude of r is less than 1, right? Okay, so as infinity, which we call just S, the infinite series, is equal to the first term times 1 minus 0 over 1 minus r, which is the first term over 1 minus r. We will play with this first. I think for today, that's what I will do. Okay, let's say, for example, take a look on number 18. We have this series 4 plus 3 plus 9 over 4 plus 27 over 16 and on. What is this equal to? If it is convergent. So the first term is 4, the ratio. But you need to make sure that it is a geometric series though. Okay, the ratio is 3 over 4. The ratio is 3 over 4. How do you get the times? Take a look. 4 times what gives you 3? Times 3, 4. Times 3, 4. Times 3, 4. Right? Okay. So the infinite sum will be the first term over 1 minus r. That's 4 over 1, 4. That's equals to 16. Now, the challenge for you is, can you write this in as the summation, using summation notation of a sequence? So the first term is 4. The ratio is 3, 4 to the power of n minus 1, right? Notice that this is the first term. This is the ratio whenever this is n minus 1. Okay? Take a look here. Take a look here. The first term, the ratio, n minus 1. In other words, one way to detect if a series is geometric series is to write it in that form. Let's say, for example, number 24. We have the sum of n from 0 to infinity of 1 over square root of 2 to the n. What is the first term? In this case, the 0th term. The 0th term is 1. And notice that I can rewrite it this way. This is from I equals to 1 to infinity. The first term is 1. And the ratio is n 1 over radical 2. Okay, so you see the ratio is 1 over radical 2. So what is the infinite sum? Infinite sum is the first term, in this case the 0 term, over 1 minus the ratio. Multiplied by radical 2 on the top and the bottom. Give me radical 2 over radical 2 minus 1. I need to rationalize further. So radical 2 times radical 2 plus 1 over 1. Oh, that's 2 plus radical. That's algebra. That's algebra. How about number 26? This infinite sum of e to the n over 3 to the n minus 1. Now notice that the way I did it here, I can easily find the first term. I can easily find the first term, right? Just set when n equals to 0 in this case, right? But how do I know that's a rational, that's a geometric series? One way to know that's a geometric series is by rewriting it into a times r to the n minus 1 form. That's one way to do it. Basically, a constant times exponential. Okay. Now, so do not assume all series you see will be geometric series. No, that's not true. That's so not true. The series that you see in this section will start with geometric series, but you will see also further that that's not the case. Okay. Now the thing is then, how do I recognize this as a geometric series? Let's see, what is the first term? The first term is e to the 1 over 3 to the 0. That's 1, that's simply e. That's the first term. But how to find the ratio? You cannot find A2 and A3 and A4 and then check the ratio all the time. What you can do is massage this series. I will first split this e to the n minus 1 times e over 3 to the n minus 1. Notice that this is the series from 1 to infinity of e times e over 3 to the n minus 1. Now, you can see better that the r is actually e over 3. So what is the infinite sum? That is equal to the first term over 1 minus the ratio. Multiplied by 3, I will get 3e over 3 minus e. But don't force it though. There are times that the ratio is greater than 1. Okay, this ratio is less than 1. This ratio is less than 1. Because e is 2.7 something, right? E is 2.7 something. If the ratio is greater than 1, then this formula does not apply. Okay, maybe I write it on the formula I have above. This formula does not apply when the magnitude of the radius is greater or equals to 1. Now from here we have a couple things to actually work with. For example, the following. I don't like to discuss it this way, but let me do it that way first. For example, something that's supposed to be discussed in Algebra 2. Decimal with repeating part is a rational number. The question is why? Let's say I randomly pick a number. For example, if I have 27.435, and on. According to the theory we learned in arithmetic and pre-algebra, it says that a decimal with repeating pattern, repeating part, can be written as a rational number. You can write it as a fraction. The question is, why? How can you do that? Now, I will show you the simple way to do this. Okay, let's say this is equals to x. Okay, set that equals to x. So this x is equals to 27.435, repeatedly, right? Notice that it repeats every 3 digits. So let me multiply x by 1000. By 1000 x. So if I multiply by 1000, then the decimal point actually moves 3 times to the right, or the number moves 3 times to the left. Is it right? Now subtract this. When I subtract this, I get negative 999 of x, and this is negative 27,408. So x is equal to 27,408 over 999. You're very likely able to reduce that. Yeah, it's reducible by 3. Okay, but at least I show you that this is already a rational number. Okay, so this is actually the fast way to find what is that as a rational number. And actually the way I do it is way too hard. That's the first way. Let me do it another way. The second way is seeing this 27.435 as 27 plus 0.435 repeatedly. I will say let y equals to the decimal part. So 1000y is 435, which when I subtract, I get, let me subtract that backward, 999y equals to 435. So y is equals to 435 over 999, and therefore 27 something is actually 435 over 900. Again, you can surely reduce that. Now, our textbook way to approach this problem is actually seeing it this way. This 27 0.435 bar can be seen as 27 plus 0.435 plus 0.000435 plus so on and so forth, in which you notice that the part from here to here you multiply by 0.001. Okay, so this is equal to 27 plus the first term 0.435 over 1 minus 0.001. Which is 27 and 435 over 999. Exactly the same answer with what we get here. This one, not really clear that they're the same. Okay, now suggested homework from here. I would like you to do number 17 from this 11.2, number 17 to number 27, number 31, number 37, number 51 to 55. Actually, you can do number 57 and on to 57 to 63. Let me show you how to do number, let's say, for example, number 62. Number 62, the question is, find x such that the series convergent. Now, what you will do is you basically rewrite it as geometric series. So this series, it starts from 0, right? It starts from 0. It starts from n equals to 0. That's the same to imagine if now I start from 1. Maybe I write it this way first then. This is sine to the n minus 1 time of x times sine x over 3 to the n minus 1 times 3. So this is the series n equals to 0 to infinity of sine x over 3 times sine x over 3 to the n minus 1. So you see, what is the first term? A sub 0 is 1. I think that one is easy. But the geometric series is convergent only when the ratio has magnitude less than 1. So the ratio, as we can see here, is sine x over 3. Now notice that this guy is always, note that absolute of r, which is absolute of sine x over 3, is always less than 1. Why? Because absolute of sine x is always less than or equals to 1. Therefore, absolute of sine x over 3 is at most 1/3, which means it is strictly less than 1. Okay, so that series happens to be a good one. Sine to the n of x over 3 to the n is convergent for all x. Okay, now here the r happens to be something I don't need to solve. I mean, it's true. It's true for all x. Let's see number 60. Remember, I don't need to worry about the starting term. I just need to worry about the ratio. Right? I just need to worry about the ratio. So let's see. The first term, when n equals to 0, that will be 1. The ratio, I need to massage this though. I need to massage this. I need to steal 1 from a -4. And then x minus 5, x minus 5 to the n minus 1. The first term doesn't matter. You will see that the first term, a sub 0, is 1. But also from here, you see, this is the ratio. The ratio is equal to -4 x minus 5. Now, the magnitude has to be less than 1. So x minus 5 in magnitude must be less than 1/4. Is that right? Maybe I write it this way first. Absolute of -4 is 4. Right? So absolute of x minus 5 is less than 1/4. Therefore, x minus 5 must be between -1/4 to 1/4. So x is between 5 minus 1/4 to 5 plus 1/4. Okay? Now you will see in future, much later, we call this interval of convergence. We call this interval of convergence. I think this is where I want to stop. On Wednesday, our greater than 1, which one? I'm sorry, the R greater than 1 is a convergent. Andre, which one you were talking about? I think